Hi, I'm Marty, and the topic for today's segment will be the standard normal distribution. Before we jump into it, just one comment I want to make about this section. It's extremely important. It lays important groundwork for the sections that follow in this chapter and the chapters that follow in the textbook. We're going to be using some of the concepts that we develop in this section throughout the remainder of the course, so it's extremely important that we learn the concepts of this section quite well. Now, in this section, we're introducing for the first time a distribution that's continuous. We're working with a continuous probability distribution. Let's just review briefly what we mean by that. In the preceding chapter, we dealt with discrete probability distributions. And they were characterized by the fact that we could add up all of the probabilities and get exactly 1. And x would typically be a counting number like 0, 1, 2, 3, and so on. And we could look at each individual probability and verify that it was a number between 0 and 1. These are requirements for a discrete probability distribution. Now, a density curve or probability density function is a graph of a continuous probability distribution. Now that we're starting to look at continuous distributions, we have two requirements, and you can see that they're quite similar to those that we had for discrete distributions. First, instead of having the individual probabilities add up to 1, now for continuous distribution we have a requirement that the total area under the curve must equal 1. And instead of having each individual probability being a number between 0 and 1, we have a requirement that every point on the curve must have a height of 0 or greater. So these are the requirements for a continuous distribution that are analogous to those for a discrete distribution. Now, in general, a normal distribution is defined by a pretty messy formula, and fortunately for us, we don't have to work with this formula specifically. If we did, though, if we had a choice of selecting any value for mu and any value for sigma, we would soon see, by thinking about it not for too long, that by letting sigma equal 1 and mu equal 0, they would be the best choices to simplify this formula as much as possible. So if you had to go home and really construct a formula or develop a graph of this equation, and it's really a graph between x and y, and you'd be free to pick anything you want for mu and sigma, you would focus pretty quickly on the fact that sigma should be 1, mu should be 0. Mathematicians have done the same thing, and we therefore define the standard normal distribution to be a normal distribution satisfying this general formula, but standard in the sense that the mean is 0 and the standard deviation is exactly 1. So a standard normal distribution is a normal probability distribution that has a mean of 0 and a standard deviation of 1, and the total area under the density curve is exactly 1, a really useful, important property. The area under this curve is exactly 1. And along this scale, we have z-scores. It's important to not confuse areas and z-scores. Z-scores are distances along a horizontal scale. Areas are areas that occur in the body of the table itself. So we have a nice correspondence between probability and area. And in this section, mathematicians have developed a special table that you have as table A-2. Two really important characteristics of this table. One is that all of the areas in the body of the table are cumulative, and they're cumulative from the left. Let's look at a specific example. We're going to look at a context that's somewhat artificial, somewhat real. We're going to consider the normal distribution of scientific thermometers, where the mean is 0 and the standard deviation is 1. I really can't draw the standard deviation like I can the location of the mean being 0. So down below here, I'm just going to make a note to myself that the standard deviation is 1. So I have a standard normal distribution because the mean is 0, standard deviation is 1. And I highly recommend that when you solve the problems of this section, for every single problem, draw a graph like this one. It's a tremendous visual help to let you understand exactly what's happening. Now, in this case, I want the probability that a scientific thermometer will have a reading less than 1.23 degrees, given that these thermometers have a normal distribution with a mean of 0 and a standard deviation of 1. Well, 1.23 is off to the right here someplace. I'm going to indicate 1.23 being in that position. So if I want a reading less than 1.23, what I'm really interested in is this area of the graph. And I could shade it in. And if you draw a similar graph, I recommend that you do the same. Shade it in to see exactly what you're looking for. Now, I'm looking for a probability of getting a reading less than 1.23. And this fantastic correspondence that we have between area and probability lets me solve the problem by simply finding the area. This area is the probability that I want. How do I find the area to the left of 1.23? Here's a small segment of Table 2. Your Table 2 is actually on 2 pages for positive z-values and for negative z-values. I've extracted a small portion of the positive part, and I want to look up the z-score of 1.23. So when I refer to my table, the 1.2 is at the left, and the 0.03 is across the top. So by intersecting the row with 1.2 and the column with 0.03, I find right here that the z-score of 1.23 gives me an area of 0.8907. So if I go back to my previous problem, I find that after looking up 1.23 in my Table 2, I find that the area to the left of 1.23 is 0.8907. That's this area right there. Now the area to the left of 1.23 is 0.8907, and therefore the probability of getting a reading less than 1.23 is 0.8907 as well. The area is the probability. We're really taking advantage of a terrific correspondence between area and probability. Now this is one type of problem we'd definitely like to be able to solve in this section. Let's consider another one. Let's find the probability of a reading greater than 1.23. Again, we'll assume that the mean is 0 and that the standard deviation is 1. We're dealing with the scientific thermometers that have the normal distribution, the mean of 0, standard deviation of 1. This time, though, if I go over to 1.23, I want the probability of a reading greater than 1.23. I'm really looking for this area. But we've stated before that for Table 2, A-2, all of the areas are cumulative from the left. So I cannot find that area from Table 2. So what do? Drop statistics and take ceramics? No, I just have to think a little bit. We've already established that the area cumulative to the left up to 1.23 is 0.8907. And we also know that the total area under this curve is exactly 1. Now think about this. If the total area is 1 and this much is 0.8907, I now have an easy way of finding the shaded area that I'm really looking for. All I have to really do is subtract from 1 0.8907. And when I do that, I get 0.1093. This 0.1093 has to be this region. Therefore, the probability of a reading greater than 1.23 degrees is 0.1093. I couldn't find this area directly from the table A-2, but I can't find it through a simple calculation. This is one thing we want to work on and be able to do quite well. Find areas of this type. Let's consider another one. This time, given the same distribution of thermometers, the mean is 0, standard deviation is 1. Always a good idea to write that so that you don't lose it. It's part of your visual field. It doesn't get lost in the shuffle. We're still familiar with that value. This time, we want the value between -1 and 1.23. Now, if I shade that in, that's this region in the middle here. I'm not going to shade it in quite yet. But, again, I want to think about how to find this middle region. Okay, but I'm given the design of Table 2 that all of my areas are cumulative from the left. Well, if I go to the table and look up 1.23, as I did before, I'm going to get 0.8907. But the 0.8907 is all of the area from this point to the left. So I'm going to write 0.8907, sort of overlapping both regions. Now if I look up -1 in table A-2, I find an area of 0.1587. For this little portion out here, it's a bit small to write. I think I'll put it up here, 0.1587. Now, think about this. This red area in here that we want, we know from here to the left is 0.8907. This much is 0.1587. Therefore, the red portion must simply be the difference between those two. That's the key point, to recognize that that's the difference between those two. So if I subtract 0.8907, subtract 0.1587, I'm going to end up with 0.7320, and this 0.7320 is the red shaded region. It is the probability of finding a reading between -1 and 1.23 degrees. So another creative use of table A-2, another way to find the probability or the area of a region, given that the table is only designed to work with cumulative areas from the left. This is the kind of thing that you definitely want to be able to practice with and do well. Now in this next example, again, we're going to take normally distributed scientific thermometers with a mean of 0, standard deviation of 1. But this time the question is fundamentally different. Instead of finding a probability, I want to find a percentile. I want to find the 90th percentile. Recall from an earlier chapter that P sub 90 indicates the 90th percentile. It's the value, in this case, the reading on a thermometer that separates the bottom 90% from the top 10%. So where would that be on the graph? Well, if I start at the left, here's the bottom 50% halfway. So if I keep going, the bottom 90% is going to be up around here someplace. I'm going to call that Z. So what is this mystery number Z that separates 0.9 to the left? Okay. But now the problem is fundamentally different than the type of problem we considered earlier. I know the area, and I want to find the score instead. So this time I'm going to go back to table 2, and I'm going to look in the body of the table for 0.9. Now, chances are you're not going to find exactly 0.9. In fact, in the body of the table, closest you're going to get is 0.8997. That's pretty close. So we'll take that as being close enough to 0.9. When we find that in the body of the table, we're looking in the body because it's already an area. Areas are in the body of the table. Corresponding to 0.8997, we're going to find that the z-score is 1.28. So that's our answer. That goes right there. The z-score of 1.28 separates the bottom 90% from the top 10%. Therefore, the 90th percentile would equal 1.28 degrees Celsius. So we've looked at a few different ways to handle table A-2, to work with table A-2. It's really absolutely critical that you get down all of the types of problems that we've discussed here. The section in the textbook has about 28 or so problems that deal with problems of the type that we're working with right here. And it would really be an excellent idea to practice and be able to do each and every one of them quite well. It's really important groundwork for the material that follows. So that concludes this section, and we'll see you next time.